I'd like to thank the Geological Society of London for inviting me today. I feel very privileged. I've been a fellow here for many years, but this is actually the first time I've been here. So the history behind me is that I worked for Shell Oil for about 16 years as a geophysicist out of college. And then in the last 20 years, I've worked for a data scientist analytical company that are more concerned about applying analytics, data-driven analytics, across many verticals, of which oil and gas is my area of expertise. So today I'm going to talk about a couple of case studies and also some of the methodologies and workflows that we apply in order to complement the more traditional way of analyzing data in the oil and gas industry, as well as doing some data-driven analytics. So the most important thing, and we've talked about data management to a certain extent, is that there's a huge amount of data out there, especially in the last few years with digital energy. Actually, digital energy has been around a long time. A lot of these companies have had their own fields of the future, etc. But there's so much data now coming out of sensor data that we get into this IoT, the Internet of Things. So there's a lot of marketing spin, and I should try and clear some of the cloud behind some of that. But the most important thing is to turn raw data, and that raw data could come from the collection of data from sensors. It can come from soft data that has been interpreted. It's time series, it's spatial data. So we need to be able to aggregate the data. So data management is certainly a key issue in trying to understand the data, not just from an interpretive, deterministic point of view, but also from a data-driven point of view. So we're trying to turn this raw data into basically actionable knowledge. And what do I mean actionable knowledge is that we can actually solve a business problem. Otherwise, we're just basically doing academic work. So most important thing is to identify a business problem and do an inverse process and turn that into a data mining problem. Many companies I visited around the globe over the last 10 years have been at different areas on the maturity scale about analytics. Some people feel like they're throwing their stuff into Excel and they're doing analytics. They may be doing bivariate or univariate analytics, but we have to look at it from a more multivariate, multidimensional, and stochastic point of view, because there's a lot of interaction, certainly in the subsurface. A lot of the analytics applied on the surface facilities are probably easier when it comes to understanding what kind of artificial lift techniques we can use, how can we optimize pumps, electrical submersible pumps, refinery, midstream, pipeline integrity. They are issues that are probably easier to understand, the low-hanging fruit. The subsurface is very complicated. As you can understand, God has put geology down there. There's rocks and stuff, petrophysical, seismic attributes that perhaps we can't control. We, however, can control some of the operational parameters that interact with that reservoir. So we'll talk about big data, and big data, I believe, a lot of people just think it's because it's a lot of data. Big data can carry many connotations. We're looking at the different varieties of data. We're also looking at the veracity of the data and the context. Context has been used many times. The velocity of the data. So now we're looking at real-time data that's coming off of sensors, and can we do analytics in real time? And I'll go through a couple of slides there to show some of the technologies that we're using. Because there's three main components here. So it's a trident with three perspectives. We have the technology, we have the methodologies, the workflows, but the most important problem is people. People are entrenched in their Newtonian physics, their mathematics, trying to resolve partial differential equations, and so they have a more skeptical outlook when it comes to data-driven analytics. But data can actually tell you a story if you know how to look through the data. This is just illustrating some of the formats of the data. So we've had hard data that we've collected in well logs, for example, seismic data, seismic attributes, core data. But now we're coming into a realm of different types of formats, different types of data sources. And we can see a few here in video and image. I've been working on some techniques that machine learning to me is something we've been doing for 20, 30 years. It's just basic logistic regression, that's machine learning. But we now need to get into some of the more higher dimension and lower dimension techniques such as deep learning. There are a lot of different ways to apply these methodologies, and these formats can actually be taken advantage of for image processing. For example, we can take seismic images in a 3D data set and just look at the actual pixelated patterns within those images and use that to train a concurrent or convolutional neural network. And I'll illustrate that in one of my case studies. We have text analytics. A lot of the data that's available now in oil and gas is actually written down, data reports, etc. So we need to be able to do text analytics and turn text analytics into more numerical data so we can aggregate the data at different levels. One thing that cannot be escaped, the understanding that we're not looking at just a bivariate relationship between temperature and pressure, for example. We're trying to understand that multivariate stochastic approach, and it's also a very multidimensional area as well. So when we develop workflows that are data-driven analytics, we try to reduce the dimension of the data, because in statistics or probability analytics, there are certain variables we call independent variables that have an impact on a dependent variable. That dependent variable is usually identified as the variable that represents the business problem. So for example, if you're looking at production data, your dependent variable may be cumulative gas or cumulative oil for that particular data set. So what are the independent variables that have a statistical impact on how to increase production? So we need to look at that, and that is an analysis in itself. So the data management and the exploration of the data are very important, because the exploration of the data will enable us to identify the relationships, the trends in the data, and the correlations between the data. And from this kind of exploration, we can reduce the dimension of the input space before we actually go and build an analytical database and also run some workflows that, for example, are doing the actual modeling. So the modeling by that, I mean, is not your traditional modeling, but more soft computing techniques, so neural networks, random forests, logistic regression, for example. Those kind of soft computing techniques need to be applied at this point. But again, we need to put this into the context, and we've heard the word context before. Context could be your Newtonian physics or your algorithms that you're familiar with as a geoscientist. When I was trained in geophysics and quantum physics, I understood there were certain mathematical and physical constraints that we need perhaps to wrap around the data-driven analytics, so we don't just create something that is totally farcical. So machine learning, you've probably heard a lot of marketing speak about what is machine learning. This slide essentially tries to encapsulate some of the techniques you've probably heard of. We tend to break it down into supervised and unsupervised techniques. So the supervised techniques is when we identify a target variable that represents our business problem. So in supervised, we have neural networks, for example, even if it's the back propagation neural network, or we're looking at deep neural networks, these are supervised so that the data is actually even more important to have as being a robust data set, because they are more sensitive to that kind of data set. You get into the unsupervised. Unsupervised is kind of part of that exploration, because we can actually use unsupervised techniques like clustering techniques. And these techniques enable us to segregate the data. And I can show you one of the case studies where we use cluster analysis, segmentation of the data, to really enable us to build out the data-driven analytical workflows that will enable us to identify which clusters contain the best wells, the worst wells, or the medium type wells. And I'll show you that in a completion study, case study, as we go through. So just one more slide really on the IT/OT aspect. So the technologies, I mean, I've heard cloud computing being used, and cloud computing is very popular now, but there's also the issue of actual cybersecurity, et cetera. You've heard of blockchain. Blockchain is now being integrated very seriously into this cybersecurity part. And if any of you own cryptocurrencies, I lost a lot of money. I bought, I think it was Bitcoin when it was about 12 bucks, and then I sold it when it was like 50 bucks. I could have waited a few more years, and I wouldn't be standing here today. But the important thing is here that we are looking at streaming analytics in our ecosystem. So streaming analytics means that we can actually put the analytics at the edge where the sensors are. We don't have to move data around. We don't have to move huge amounts of data to a database that may be sitting remotely many miles away from where the data is actually being collected. So now more and more people, companies like Rockwell, et cetera, are putting sensors, and they're actually putting analytics. And OSI SoftPi have come up with some historian where you can actually implant the analytics into the historian, and as the data is being collected, we can do the analysis there and actually not move the data as much. In motion analytics means, okay, we're getting it from the historian, we're moving it now towards maybe an analytical center of excellence. I worked for Shell down in the Gulf of Mexico, and we have this analytical center of excellence in New Orleans, but all the data's coming off the rigs in the Gulf of Mexico. So as the data's being moved through fiber optics or across the wire, we can actually do the analytics as well in the process. That analytics is primarily to try to reduce the input space again. Do we need all these data sets, and what kind of data sets do we need? And that's a discussion between data scientists and the business people. The most important thing to realize is that the business people, the domain experts, those who are being educated in geophysics, geology, reservoir engineering, production engineering, they're key to everything. The SMEs are there to ensure that along the steps of data-driven analytics, we're keeping everything within the context of first principles, for example. And then we have the REST analytics. So this is when the analytics is actually done in the center of excellence. So this would be onshore, for example, if we're doing a lot of data collection from the Gulf of Mexico off all the rigs, the data will be coming into this supercomputer that is onshore, and then we can do the analytics there as well. So we've got 3 areas where we can actually apply analytics and come up with some insights into the data, because it's all about pattern recognition. Pattern recognition is the key behind everything that we're doing in data mining. And so we need to look for those patterns, but those patterns really are identified by the business people. And one of my illustrations here on the seismic, I'll explain again in more detail what I mean by that. So this is the first of the 3 case studies. So in this situation, we're trying to automate a fault detection solution. So again, we have the traditional way of working. When I was a geophysicist at Shell, they used to give me like 50 yellow crayons. And then what I would do, I'd get my seismic sections, the inlines and the cross lines, and I would be trying to follow the horizons across faults and stratigraphic traps and structural problems, and then try to digitize that as the areas that we potentially could drill. But when we went through that whole process, collecting the 3D seismic data, breaking it down into inlines, cross lines, time slices, etc., we found that after the traditional processing techniques of deconvolution, migration, pre-stack, post-stack stuff, that took a long time. We didn't actually do the interpretation until about 6 months later. So what we try to do here, and we've been working with MIT on this situation because They claim they're smart people up there, but what we try to do is maybe bypass some of that, but not actually exclude the work done in the traditional way, but we try to complement that so that perhaps we can add other insights into the interpretation. Because I remember working with a guy from Exxon. He's actually an ex-Exxon. He was working in Saudi Aramco when I was in Aramco many years ago. And he came out and he was dressed like some kind of hippie. He was like 70 years old. And he claimed he was the world's expert on free water level. So he was very skeptical about what we were trying to do. So we took a lot of their production data, reservoir data, a lot of the different seismic attributes that we could generate, basically a lot of the spatial and temporal data that we could aggregate, and we were trying to identify where the free water level was, because they were having problems in water flooding in Saudi Aramco, because in Aramco, as you probably know, they've been flooding those reservoirs for about 70 years. But quite often they don't understand where the thief zones are, where the faulting is. And some of the injector wells were just not doing a good job, and production was going down, water cuts were very high. So we did a data-driven analytical approach, bringing in all their different data sets. And we could actually show the guy, okay, I don't think you appreciate where that free water level is, and you got your injectors probably in the wrong place. Now, he didn't take too kindly to that, but he realized that we were giving him a different perspective. He was being asked questions by the data. The data has actually been through that reservoir, the production data, and it has a story. It has fingerprints. It has signatures in the data. And can we read those signatures and patterns and then complement that with their geologic model? And it worked out pretty successfully. In this case, we were using images, seismic images. So that was a process of talking to the geophysicists, asking them, okay, which are the direct hydrocarbon indicators? What is the features? What are the patterns? What are the pixels that represent, for example, a DHI or a stratigraphic trap? And they have proof, because they've obviously drilled quite a lot of successful wells. Saudi, as you probably know, make a lot of money drilling in the Gower field, for example. We worked in the Gower field. And so we were really looking to see if we could get some other insight into that data that would be different from their traditional interpretation. And can we automate or semi-automate some of those processes? Data management can actually be automated or semi-automated when it comes to aggregating different data sets at different scales. But when it comes to the decision-making, which is something we really wanted to break down at a much faster scale, we could actually reduce the decision-making cycle from 3 months to about 3 weeks. And those decision-making aspects were very important, because what we use is a lot of more data they don't usually use other than through their traditional interpretation. We took the pixelated inlines and crosslines of the 3D, generated some seismic attributes, and these were inputs into a neural network, a deep neural network, a convolutional neural network that was trained to identify these similar patterns elsewhere. So then, like in a radiologist report, if you go to a doctor and he's looking for disease, for example, instead of looking at thousands and thousands of MRIs, CAT scans, PET scans, we can actually say, let's look at only these dozen, because we've identified similar patterns that are indicative of disease, or in this case, indicative of DHIs. Maybe you need to concentrate on those areas before you go wandering off or ignoring other data, because we found that they're only using about 20% of their data. Now we could use 100% of their data, and through these techniques say, okay, we can ignore that 60% of that data, focus here on looking to re-engineer your field with new injector, new production wells. The second one I'm going to go through is a completion study. In the United States, we do obviously with a lot of hydraulic fracture strategy techniques. And so I was working with Shell. This is a public paper, by the way. And with Shell, they were looking to optimize their hydraulic fracture strategy. How much proppant or frac fluid do we need? what is the number of perforations? What is the number of stages? Now, this came from a Wyoming pine dow asset. It's an anticlinal structure, and we decided that where to stick the next wellbore to get maximum gas production. So we looked at all their historical data, and that's the key, looking at all the historical data and trying to analyze that to look for patterns and relationships between these different variables and come up with a statistical model that would perhaps predict or forecast and provide prescriptive analytics that it enables you to make decision-making more quickly. So what they did, they had thousands of wells, and they needed to normalize these wells. So we spoke to the geoscientists and said the best way to do that is to use PLT data. So they had PLT data, production logging tool data, and some of that was telling us which of these stages were producing water, which was producing gas. So that enabled us then to normalize the start of every well from 100 days out from when PLT data was collected. So we created a new variable called QG100, which is cumulative gas 100 days after PLT data had been collected. We then looked at all the different reservoir properties, operational properties, and some of the petrophysical properties. And also we got into the mathematics of it. We used some Laplacian second derivatives to try and locate the next wellbore across this anticlinal structure using some kind of non-Euclidean mathematics. And it turned out that instead of just going with their cookie-cut template of, okay, these are the operational parameters we're going to use in order to drill the next well, let's use some of these data-driven analytics that is telling us that the best wells, and I'll show you here the neural network that we use. As you can see in category 1, 2, and 3, these were the outputs from the neural network. So we're trying to find more wells that had basically category 3 production. Now, I mentioned cluster analysis, I mentioned segmentation. These were techniques that were used to try and characterize the wells, not from every aspect, from all the data sets that were input. And so we used the, as you can see on the green side, these are the input nodes. And then we had the neurons that would then tell us, once we've trained this neural network, we could then bring in some new data, and they would tell us which category that well would fall into based off of the selection of the operational parameters we were going to use for that particular wellbore. And then we could only stick with the category 3s, and so that's what they drilled, the category 3s. And the ROI was quite incredible. For the price of about $400,000 or $500,000, they now produce about 15% more by volume of gas from this particular anticlinal structure. My last case study is more around the artificial lift technique. So we're moving now further up the well, but a lot of the wells in the United States now, and probably in the Middle East where I went to visit recently, are being censored. So there's more intelligent wells out there collecting fiber optic type data like distributed temperature, distributed acoustic data. And so all these different types of temporal time series data and spatial data are all part of this process that enables us to come up with a really good, fast decision-making analytical approach. But again, we still need the geoscientists. We're not trying to put them out. It's not a black box. We don't want a black box. We want them to be able to interact with this and say at this stage, well, this doesn't make sense. I think you're overfitting the model, et cetera, et cetera. In the case of the ESPs, they were getting a lot of failures. They were buying these ESPs from companies, and these electrical submersible pumps were basically not performing. They were tested in labs. They came up with a preventative schedule for maintenance, but was that a very good schedule? And so what we wanted to do is understand from all the historical ESPs that have been implemented in the Gulf of Mexico was what are the signatures, what are the characteristics of certain variables like temperature, like pressure? What are the most important variables that impact the performance of that pump? And so we could collect that data through all the different historical analysis and do a root cause analysis and identify the most important signatures. And so then that had a predictive value, because we could then, in real time, bring in new data from new pumps. And if we saw that these particular relationships between the most important variables were falling above an upper or lower boundary, then the performance was not as good as it should be. So we want to increase the life cycle of these pumps that cost over $1 million. Or can we find an idea where there's going to be a catastrophic event? Catastrophic event is something that happens in time and space, and that event may cause the pump to fail, and the MPT are closing down that well for about 3 months sometimes, anywhere from 3 weeks to 3 months, because if they haven't got the pump on the rig, then they have to order it, etc. So the intention was to use these techniques, these data-driven analytics, to prevent the actual MPT from being so long, so they could actually order a pump just in case there was a failure. And they were so skeptical in the engineering department in Shell in the Gulf of Mexico that they actually let one fail, and we predicted that it would fail probably six weeks before it did, but at least they brought the pump to the rig, so MPT was reduced to a certain extent. This is just to illustrate the value of the theoretical, actual, and the equations that we use. As you can see, the orange one is what the vendor of the ESP pump provided to Shell and said, essentially, this is how your pump will perform over this course of period. And the actual green is how it did perform. And with predictive analytics, based off of historical data, you can see the red where we were more close to understanding the actual performance. My last slide is basically just to illustrate, to drive over the point that we need to convert disparate EMP data into knowledge, and there are multiple data sets, and there are multiple workflows that are data-driven that we can implement in order to try and improve the value of the data, build predictive models, operationalize those models, and then during that whole process from beginning to end, we need the SMEs to come in with their physics and mathematics to make sure that we are within a certain confidence limits, so that we're not actually creating something that's just pure magic. Thank you very much.